Hi, and welcome to Math 232. This is section 3.1, operations on matrices. Okay, so what we're going to do here is basically learn about some of the properties of a matrix, how we talk about them, how we use them, and they have properties sort of independent of where they came from. As we've seen, they can come from systems of linear equations, but they can also come from other types of things, and they have properties independent of where we got these things from. Okay, so the main vocabulary word here is matrix, and that just simply means a rectangular array of numbers. So here it is here. There's a matrix. The matrix is typically going to be titled, labeled with a capital letter, and there's a rectangular array here, and we'll notice here that we've got m rows. So this is here m rows. M rows. So each one of these guys here is a row, and there are m of them, and you can tell that because this thing here is an m. And there are going to be in this matrix here, there are n columns. So when we indicate the size of the matrix, we say the matrix A is of size m by n, and we always put the rows first and the columns second. So if I were to write like this, A 3 by 2, that would mean the matrix called A, which has 3 rows and 2 columns. Okay, sometimes we can use slightly different notation. Sometimes we will use the notation like this, the matrix with entries A sub I sub j, I keep the square bracket, I sub j of size m by n. Sometimes we will omit that. The size indicator here will just say the matrix A, which consists of the entries A, I, J. Okay. This symbol here represents the entry in the matrix capital A, which is in row I and column J. Okay, and two matrices are equal if they have the same size and every entry is the same. Okay, let's just take a look at a couple of examples here. Here's an example. We imagine the matrix A looking like this: 1, 2, 3, -4, -5, -6. So this is a matrix with 2 rows and 3 columns. So this is a 2 by 3 matrix. We could indicate the individual entries in this manner. The entry A11 is 1. And that is in the first row, first column. And then in the first row, second column is the number 2. In the first row, third column is the number 3. Similarly, in the second row, first column is the number -4. In the second row, second column, -5. And in the second row, third column is -6. So just to make sure that you understand that the first index is rows, the second index is column. Sometimes we would then write like this: the matrix A, entry row 2, column 1, -4. The matrix A, row 3, row 2, column 3. The entry is -6. Okay. A square matrix, that is n is equal to m, the same number of rows as columns, then it is square. So that is, I think, fairly obvious. And we'll just note, of course, when it's square, then this will be NN here. And we have special entries these entries here are on the diagonal. So those entries there are the entries there on that is the main diagonal. So those are the ones where the row index and column index are the same. So let's just give an example. Here we have some matrix here: 4, 5, 6, 7, 8, 9. This is a square. This is square. It is 3 by 3. And these are the entries on the main diagonal: 1, 5, and 9. Okay, if we have a square matrix where the entries off the main diagonal are 0, we call it a diagonal matrix. So we have, in this case, we have here that the entries here that are not on the main diagonal are all 0. So this guy is a diagonal matrix. So here's another one. 1, 2, 3, 0, 0, 0, 0, 0, 0. Move the 3 over there to line up a little bit better. Okay, so there's a diagonal matrix. We also have triangular matrices. A triangular matrix is a square matrix where either all the entries above or all the entries below the main diagonal are 0, but not necessarily both. Okay, so we have upper triangular and we have lower triangular. Let's just see what those features are. If we have this situation where we have all these guys being 0, so we identify the main diagonal. Let me just draw a line through the main diagonal in both cases. That's the main diagonal. And then we look at the off diagonal entries. If they are all 0 below the main diagonal, like in the case of the first one on the left here, then we call this one here upper triangular. It means basically the numbers are in the upper triangle. Okay, so we have a triangle up there. Let me just make it in, say, black. We have a triangle here. It's in the upper part, and that's where all the numbers are. Similarly, in this one down over here, we have all the numbers in a triangle in the lower part down here, and we have all the numbers up here are 0. This one here, this matrix here is lower triangular. Okay, we can specify that with our element entry by saying A is upper triangular if all the entries A, I, J are 0 for every I greater than J. And it's lower triangular if A sub I, J is 0 for every J greater than I. So now we have a concept. We have the fact that a matrix is a rectangular array of numbers. We have that if the matrix has the same number of rows and columns, it's a square matrix. We have the concept of a diagonal matrix, and we have a concept of an upper and a lower triangular matrix. The answer to this question here is, can a matrix be both upper and lower triangular? The answer to that is yes, and that it equals the diagonal matrix. Okay, so for example, we have we could have this kind of matrix. I think I've already used this example, in fact. Okay, so this is upper triangular, it is lower triangular, and it is also diagonal. Okay, we're going to see a little bit later, but let's just bring this up right now. We have, of course, the possibility of a diagonal matrix where all the diagonal entries are 1. So now let's take a look at, consider a diagonal matrix where all the diagonal entries are 1. Okay, let's just take, like, I'm going to call it this I. There's the 2 by 2 flavor of that. It's diagonal matrix and both diagonal entries are 1. This is called the identity matrix. This is the 2 by 2. We could call it I2. The 2 by 2 identity matrix. And then, for example, I3, unsurprisingly, I think, looks like this. Okay, it's 3 by 3, and all the diagonal entries are 1. And this just keeps going. No, 4 is 4 by 4 with all of them. So this is the identity matrix. Okay, equality. I think I mentioned this already. If A and B, A is equal to B, we have two matrices, they're equal to one another if they're the same size, and all the entries are equal. Okay, that's not too hard to figure out. It basically means if we've got these two matrices that are described with this format right here, we have that M is going to be equal to R, N is going to be equal to S, and Aij is going to be equal to Bij for all I and J. This cool little symbol here means for all. Okay, so rectangular array of numbers is a matrix, and then there's some words that we use and symbols that we use to describe the matrix itself and the entries into the matrix. Okay, now what we're going to do first is we're going to learn how to add, subtract, and do scalar multiplication for these guys. This is very similar to what we did with vectors. That's the first thing we did, learn how to add and subtract them, and then learn how to do scalar multiplication. So if the matrices are the same size and C is a scalar, then we simply add the entries, or if we want to add the two matrices, or we subtract the entries if we want to subtract the two matrices. And if we try to multiply by a scalar, we multiply every element in the matrix by that scalar. Okay, for addition of matrices or subtraction of matrices, the matrices have to have the same size. Otherwise, the operation is not defined. A couple of examples. Now, I think this is a straightforward operation. So if you have said, okay, I see how this works, not too complicated, stop the video right now, do these calculations, and then turn it back on and quickly check. A plus B. That's not defined. They're not the same size. A plus D. That looks like this. 207 minus 543. That is A. And then we're going to add to it D. 649,358. We're going to add those two things together. And so we take this guy plus this guy, we get 8. Then we take, it's got a different color here. We take this guy plus this guy and get 3. We take this guy plus this guy and get 11. We keep going like this. This guy is 0. 4 plus 9 is 13. And 8 plus 3 is 11. There we go. Okay, so that's how we add. If I take a look here at what is B minus D, not defined. They're not the same size. So I can't do it. If I take C minus B, then I look, they're the same size. There's C and B right there, they're the same size. So I can do this operation. So I have 1, 2, 3, 0 minus 1, 0. I subtract from it 4 minus 3, 0, 1, 5 minus 1. And I get 1 minus 4 is minus 3. 2 minus 3 is 5, etc. 3 minus 0 is 3. And then continuing that same process on the second line, I get these numbers here. Okay, that's subtraction, addition and subtraction. Next one, multiplication by a scalar, 5 times A. So I take 5 times and I write down the matrix A. There it is. And I simply multiply every entry in the matrix by 5. So I'm going 2 times 5 is 10. 5 times 7 is 35. 5 times 4 is 20, etc. I multiply each one of them by 5. There it is. And I mean, just doesn't actually, no, the process is no different. If the scalar, these guys are scalars, they're just numbers. If the scalar is negative, but let's just do an example. That was going to be, I'm going to do -2 times B. So I'm just going to take B. I'm writing out the elements of B now, and then I'm going to multiply each one of them by -2. There it is. Okay, so I've multiplied by a scalar. I know how to add and subtract. Okay, we're going to realize that as we go along, we're going to be thinking of matrices sometimes in different ways. So we can think of a matrix as a list of row or column vectors, or we can think of it as a list, we can think of it as a list of column vectors, or we can think of it as a list of row vectors. What does this mean? If I have a matrix that looks like this, 1, 2, 3, 4, 5, 6, I can sort of be thinking of that like this. A list of column vectors. And that would be where I'm thinking of C1 as the first column, 1, 3, 5, and C2 as the second column. Now you notice that C1 and C2 are vectors. So if I have these two vectors, I could say to myself, oh, I'm going to make a matrix out of these two vectors by putting those two vectors into the matrix as columns. Similarly, I could be thinking this way, 1, 2, 3, 4, 5, 6, like this. I could be thinking of this as a list of row vectors. I could be thinking of it this way, where row 1 is 1, 2, row 2 is 3, 4, and row 3 is 5, 6. So if I had these three vectors here and I wanted to make a matrix, I could say, hey, I'm going to take those three vectors and I'm going to put them into a matrix where each one of those vectors is a row. So we can be thinking, that's what this is telling us here in general. We could be thinking of A as a list of columns or as a list of rows. Okay, so we're just going to quickly write out the row and column vectors of A. Good. Another good chance to stop the video and just make sure that you've understood the explanation by attempting to do the exercise here. So I would write this in this manner. Column 1 of A. Let's see, what is column 1 of A? It is 3, 2, 1. Column 2 of A is 0, 9, 8. Column 3, notice these are vectors. Column 3 of A is 7, 6, 1. Column 4 of A is 5, 0, 4. Row 1 of A, that's the first row. It's also going to be a vector. It is 3, 0, 7, 5. Okay, this just continues on. Oh, for completeness, I'm going to do these all. 2, 9, 6, 0. And row 3 of A is 1, 8, 1, 4. There we go. Okay, so here A can be thought of here as column 1, column 2, column 3, column 4, which is a row of column vectors. And I could be thinking of A as R1, R2, and R3, which is a column of row vectors. When we solve problems later in this course, we will sometimes be wanting to know something about vectors. And in order to figure that out, we will be forming a matrix. And sometimes we will put the vectors into the matrix as columns, and other times we will put them in as rows. This often leads to a bit of confusion. So it's a good idea now to get straight that we can do it in both ways. And there will be different things that you can see by which choice you make. Okay, let's talk about span and linear independence for matrices. The last time we talked about span and linear independence, it was about vectors. So that, look, compare, in some sense, compare with what you already know, compare it with vectors. We did span and linear independence of vectors. Now we're going to take a look and say, well, if we have a collection, a set of matrices, what does it mean to span and what does it mean to be linearly independent? And they follow exactly with just a little bit of scaling up of the idea from the definitions we had for the vectors. So we take a set of matrices and the span is defined analogously. The span is all linear combinations of the matrices in our set. That's the span. And the set of matrices is linearly independent if the only solution to multiplying each matrix by a scalar and adding them all together, if that's equal to 0 only in the case where all the constants are equal to 0, then the set of matrices is linearly independent. Okay, so we're going to take an example here. I think this is the best way to see about this. Here we have a set of matrices. There's 3 matrices in the set. Each matrix is 2 by 2. And we're going to determine, is it linearly independent? And further, is this new matrix, is that in the span? That's what we're going to ask ourselves. So first of all, the first question we're going to take a look at is the linear independence question. We're asking, are there constants? Are there constants C1, C2, C3, non-zero, such that C1 times the first matrix plus C2 times the second matrix plus C3 times the third matrix is equal to 0. In this case, 0 is the 0 matrix. Okay, so let's just take a look at what that, let's now actually, so this next step to do here is to take this and perform this operation. So we're going to add those three matrices together, and we get, when we recall when we're doing scalar multiplication, this is going to be multiplied into all four of these, and then we're going to add together. Okay, so our first entry here is going to be C1 plus C3. And then this entry here will be 2C1 plus C2 plus C3. This one will be C1 minus C2 plus 3C3 and 2C2 minus C3, like that. And we're asking for what values of those things are these guys all equal to 0. Okay, so make sure you'll be sure that you've understood scalar multiplication and addition if you can take this statement right here and turn it into that guy right there. And now we're going to ask, when does this equal 0? For what values of the c's does this thing equal 0? Well, look what's happened here. We've got 4 equations and 4 unknowns. Okay, we've got this thing here has to be 0 because for two matrices to be equal, all of their entries have to be equal. So for this guy on the left to be the 0 matrix, each one of the entries in the matrix has to be 0. So that tells me that C1 plus C3 must be 0, that 2C1 plus C2 plus C3 must be 0, C1 minus C2 plus 3C3 must be 0, and finally that 2C2 minus C3 is equal to 0. Okay, so I've got 3 unknowns and 4 equations. I can now set up a new matrix that I'm going to row reduce in order to find the values of C1, C2, and C3. So I basically here got 4 equations, 3 unknowns. And at this point, we can sort of forget that it came from trying to figure out this problem. Now, also this portion of it is to say, let me figure out what these C1, C2, and C3 are. And then once I know that, let me use those numbers to understand, is the original question, are these 3 matrices linearly independent? Okay, so I'm going to go ahead and put the matrix here to be row reduced. It looks like this. Okay, make sure, possibly by stopping the video and trying, that you can take these set of equations and turn it into this augmented matrix. You have to be able to do this. We're going to be doing this all of the time. Now what we're going to do is use Gaussian elimination to put this into reduced echelon form. So I'm going to go ahead, I'm going to write the first one out here, but I'm looking at making zeros here, right? So what am I going to do? I'm going to take row 2 and replace it by row 2 minus 2R1. Again, why don't you stop and do the Gaussian elimination? I'm going to do all 3 of these guys in the first one. So I'm here. And then I take R2 minus 2R1. And then I take R3 minus R1. Then I take I just leave R4 alone. Don't have to do anything. The 0 is already there. Okay, so I've got all zeros here. I've got a leading one here, and I've got a leading one here. Now I have to make these 2 numbers into 0. So I continue with the Gaussian elimination, and I get the first row is fine. I don't need to do anything. Second row, fine. And then I take R3 plus R2, and I get, and then I take R4 minus 2R2, and I get this. Again, if you're not sure, stop and practice the elimination until you can get the Gaussian elimination done. I stop. I mean, I guess I could make this guy into a 0 as well, but I don't even really need to do that at this point because I can see what's going on at this point. And that is, these two lines are telling me exactly the same thing. They're telling me that C3 is got to be 0. This one is telling me that C2 is equal to C3, which then is 0. And then this line here is telling me that C1 is equal to minus C3, and we know that C3 is 0. So I found out that the only solution is C1 equals C2 equals C3 equals 0. Therefore, the three matrices are linearly independent. Okay, it means that you cannot make one of the matrices out of a linear combination of the other two. Okay, now the next question is this guy here 2, 3, 2 minus 3 in the span of those three matrices? Okay, this is in somewhat quite a similar question, like slightly different. It means, does 2, 3, 2 minus 3 equal T1, 1, 2, 1, 0 plus T2, 0, 1, minus 1, 2 plus T3, 1, 1, 3 minus 1 for some values of T1, T2, and T3. The difference, of course, is that this is not 0. So I'm asking, are there some values of T1, T2, and T3 so that this equation can be true? There may or may not be values of T1, T2, and T3 that make this happen. Okay, so I do the same thing I did before. I perform this addition. This is the same addition that I performed last time, except I've used T instead of C. So I'm going to get these same equations that I had here. And then I can form the augmented matrix, which will be exactly the same as this augmented matrix, except this will not be 0 anymore because this is not 0. Okay, so let me just write out for you what the augmented matrix is. Here it is. 1, 0, 1, 2, 2, 1, 1, 3, 1, minus 1, 3, 2, and 0, 2, minus 1, minus 3. Okay, so it is, I'm just going to change colors to highlight this. It is the same matrix as we have here, with the exception that this final column is different. Okay, you see the final column is different because last time we were checking if those things were, if we were able to form the 0 matrix. Now we're checking, is it possible for us to form this matrix here? So you proceed with the Gaussian elimination, which will be exactly the same set of steps, except now you have to do the arithmetic on this side, which was previously 0. So I'll leave that to you as an exercise, and we will simply get this row echelon form matrix. I highly recommend, of course, you stop, you do that, and make sure that you get this. Possibly I've made an error. If that's the case, let me know. Or you can check your own work and make sure that you can do this. What does this tell me? This tells me that T3 is equal to minus 1. T2 is equal to minus 2. And T1 is equal to 3. So yes, that matrix is in the span, and there are the constants. Now, what you can do in this case is very, very easily check that you've got the right answer. Let me just write out what that looks like. So I got, my screen went a bit small there. Let me just get the black here. Okay, what do I mean by that? How do I check? I now know the value of those constants, I believe, and I'm going to make sure I did it correctly. So I'm checking. So this is a check. Here, we're just cleared some space for myself to check. And I'm checking 2, 3, 2 minus 3. Does that equal 3 times, that's T1, 3 times 1, 2, 1, 0, minus 2, that's T2, times 0, 1, minus 1, 2, minus T3 minus 1 times 1, 1, 3 minus 1. There it is. Okay, and then you can easily do this. I'll just do one of the 4 of them. You can do the other 3. I check 2. Is that equal to 3 minus 0 minus 1? Yes, it is. Then I go through the other 3 elements, and then because I can make this guy out of these 3, out of a linear combination of these 3, then I say, yes, this guy here is in the span of these guys here. It's exactly like it was for vectors, except that we are dealing with a slightly different object. Right, the next thing we're going to touch on here, and we're going to use this more later in the course, we're going to touch on what is a transpose. So a transpose, which we denote by this symbol here, A with a capital T superscript, it's the n by m. Notice these are in the opposite order that you see them, created by making the rows of A into columns. Okay, so this is simple once you see it. That looks like this. A transpose. Okay, here's A. So A has 2 rows. So A transpose will have 2 columns, and the columns will be the rows of A. So this first row here becomes the first column here. And then this second row here, becomes the second column here. There you go. Okay. Similarly, let's just you'll see B is a 1 by 3 matrix. Vectors are, in some sense, we can think of vectors as matrices. They just have either 1 row or 1 column. So I'm going to take B and I'm going to write B transpose, and that is going to simply be like this: 8, 7, 1. Okay. So the rows of B have been made into the columns of B transpose. And if I take the transpose again, I take B transpose transpose, that's going to be taking this guy, 8, 7, 1, that's B transpose, and I'm going to take the transpose of that, and I'm going to get 8, 7, 1. So B transpose transpose is B. And that's, of course, true in general. And that's in general. All right. That's something you should know. Somebody says, take the transpose, you have to know what to do. It's a vocabulary word. I probably should have added it to my vocabulary for this lecture. Okay, now we're going to come, what we're leading up to here is how do we multiply together matrices? We're going to start first by taking a matrix and multiplying it by a vector. You'll note that the vector multiplication was not trivial. We had 2 types of vector multiplication, a dot product and a cross product, and we are for the most part exclusively focusing on the dot product. And interestingly, the dot product of 2 vectors was a scalar. So now what we're going to be doing is taking a matrix and multiplying it by a vector. So we're just going to sort of set the stage here by thinking about a linear system. So we have a linear system here, and we can think about this in the following way. We can form a coefficient matrix, which is going to be the coefficients of the variables of our linear system. So this will look like this: 3, minus 7, and 1. That's the first equation. And then the second equation coefficients are 5, 1, and 2. Then we will make a column vector, which has the components of which each component is one of our variables. And then we will have the vector on the right hand side, which is very typically called B, this little B, and it will have the elements in for 2. Okay. And what we want to do is be able to see that this is the same as this. So when we take the matrix A, which we just did, and multiply it by X, which is this guy here, we will get B. So this system of linear equations can be reformulated as AX equals B, where we have A, X, and B defined here. So, right, this is what I have effectively just reset. Okay, so let us let's just take an example here. Let's take a slightly, well, the small, sort of the smallest possible example. There. Here's two equations, two unknowns. As we've learned from before, the augmented matrix looks like this. 2, 3, 5, 7, minus 2, 4. And we, of course, can solve this system by using Gaussian elimination on the augmented matrix. Right now, however, let us write out A like this, 2, 3. This is now the coefficient matrix. And then let us get these two vectors here, x1 and x2, and the vector B, 5, 4. Okay, so, and now we want to take this and write and say it is this, AX equals B. That means AX, a matrix, times a vector is equal to a vector. That's what we're trying to do here. We can think of it like this, as x1 times the first column plus x2 times the second column is equal to the, so we can think of this vector here, which I put here, as a linear combination of the columns of A. These are the columns of A. And what we're doing, we're taking a linear combination of the columns of A. The other way we can think of this is we can, and we're going to go through this again in detail. We could be thinking, in some sense, this is our type of multiplication. We take the first row of the matrix and we multiply by the first column. That gives us 2x1 plus 3x2 equals 5. Then we take the second row of the matrix and we take that into the first column and we get 7x1 minus 2x2 is equal to 4. Okay, so we're going to state this as a definition and then we're going to look at a couple of ways we can interpret it. Here is the definition. The product AX. This is matrix A multiplied by vector X. Okay, so there it is in an m by n matrix and a n column vector. So we take the first row of the matrix and we multiply, we basically form the dot product with the vector. Then we take the second row and we form the dot product with the vector and we get this guy here. Okay, we proceed on to do that for each one of the rows of A. We form the dot product with X and we make that as a number in one of the columns of B. Okay, this process is not always defined. The sizes have to be correct. So here we have, well, let's do an example where we'll show how the sizes need to match. Here's an example. We will multiply the matrix 1, 2, minus 1, 0, 3, 2, 4, 5, 3. We're going to multiply that by the vector 2, 1, 0. Okay, first we check that if the sizes are right. Here's what you can do. This is a 3 by 3 matrix, and you can be thinking of this as a 3 by 1 matrix. Okay, and what has to happen is that these two numbers have to be the same. Otherwise, the multiplication won't work. Not only that, once those two numbers, you've determined that those two numbers are the same, the resulting object that you get will be of this size, 3 by 1. So over here, we're expecting 3 by 1 over here. Okay, so let's take a look at this and see what happens. We take this row into this column, we're forming that dot product. So we get 2, that's 1 times 2, plus 2 times 1, minus plus 0, minus 1 times 0. And then the next one, we take this row and we dot product it with this column here and we get 0 plus 3 plus 0. And then we take the third row here and we form the dot product with this guy here and we get 8 plus 5 plus 0. We perform that arithmetic and we get 4, 3, and 13. And you will notice that this, we move this over right underneath, is a 3 by 1, 3 rows, 1 column. Okay, as I said before, we can also be seeing this as a linear combination. So we can view AX as the linear combination of the column vectors of X as per the linear combination of the column vectors of A as per the coefficients that we see in X. Let's just write that out with using the same example, using an example, a 3 by 3 example. Okay, right now, these could be numbers, but right now they're just not specified. So we're thinking of this as some amount of column 1 plus some amount x2 of column 2, some amount of column 3. Okay, that's another way. So those are the columns, and then we take a certain amount of each one. Okay, I use the dot product explanation when I was doing it right from the definition, but this is just written out explicitly. We see that the A times X is the first row of A dot product with X, and then the next number, the next entry in the column vector that results is the second row of A taking dot product with X, and so on. Okay, so yeah, maybe what you can do is take one of these 2 examples above, or even maybe both, like that, and sort of be thinking of it in this manner and make sure that you get the same result. It doesn't matter how you're thinking about it, it's just a different way of thinking about it. You always, of course, get the same result. We'll do an example. We're going to evaluate the following using all 3 methods. Okay, of course, good time to stop, try to do this multiplication yourself, and see that you get the correct answer. So I'm thinking row 1 into column 1, and then row 2 into column 2. So I'm going by the definition. The definition, I'm going to be thinking of it this way. 5, 0, 2, minus 1, 4, 1. 3 minus 2, 10. I'm thinking of it then this way. 5 times 3 plus 0 times minus 2 plus 2 times 10. Okay, first row into the first column. That's the way I say that. And then I take this row 2. Sorry, this is not into column 2. There's no column 2, into column 1. Let me do that. That is minus 1. I'm going from here, this guy into here, minus 1 times 3 plus 4 times minus 2 plus 1 times 10. I perform that arithmetic and I get this number. Okay, no way. Then I think, okay, let me think of it as a linear combination of columns. Then I'm thinking this way. I'm thinking of doing this multiplication, and I'm thinking in the linear combination of columns idea. And what I do is I think, okay, that's fine. I'm taking 3 of the first column, minus 2 of the second column, and 10 of the third column. And I perform this. This is now a linear combination of vectors. We already know how to do this. So I perform that and I get 35, and I get 3 minus 8 plus 10. I get, see how I've got a different answer than here. It's 3 minus 8 plus 10. Hang on, minus 3 minus 8 plus 10. Let's see. It's like I have some sort of an error. Did I copy something down wrong? Hang on, I'm quickly doing this. Minus 1 times 3, 4 times minus 2, 1 times 10. That is minus 3 minus 8. It's minus 11. Oh, this should be a minus 1. Okay, here I've got 3 of the first column. Oh, there's the -1 is missing there. Okay. And then I get a minus there. Okay, now I'm here -1. Okay, now they agree. Sorry about that. I lost a couple of negative signs. Okay, now I'm doing it with the dot product. I'm thinking of it this way. The dot product of 5, 0, 2 with 3 minus 2, 10. The dot product of with 3 minus 2, 10. Yeah, those two dot products. And I get the same thing. There it is. Okay, so that is multiplying a matrix times a vector. Now we're going to scale that up to the product AB. So this is multiplying one matrix times another one. Okay, so here it is. It's defined in this way. It is defined as a number of columns of matrix vector multiplications, which you already know how to do. So the first column here is A times column 1 of B. Then the second column here is A times column 2 of B. Let's not focus maybe too much on this definition. It's correct, of course, but let's just see an example. I think that makes it more straightforward. So we're going to multiply A times B. And so I'm going to write them down. There they are. There's A. And I'm going to multiply that by B. Okay, first thing I gotta do is check that I can do this. And here's how you're going to do that. You're going to write out that this guy here is a 2 by 3 matrix A, and B is a 3 by 4 matrix. Okay, and then the inner numbers have to match. These two guys have to be the same. They are. Proceed. If they're not, write out that the product is not possible and go to the next question. Also, I know what the resulting size is going to be over here. I know it's going to be 2 by 4. So the resulting matrix is going to be 2 by 4. If it's not for some reason, then you know you've made a mistake. Okay, so let us see how I do that. I come here and I take the first row into the first column. So I say 4 times 1 plus 0 times 0 plus 5 times 2. I get here 14. I take the first row into the second column. I get 4 times 10 plus 0 times 6 plus 5 times 2. This number here is 50. I take the first row into the third column, get minus 43. I take the first row into the fourth column, I get 45. Okay, then I move to the next row. I take the second row into the first column. So I get 3 times 1 plus 0 times minus 2 plus 8 times 2. And that gives me 19. Then I take that first row and I go into the second column. 3 times 10 minus 2 times 6 plus 8 times 2. I get 34. Continuing this pattern, I get this. Okay, stop the video. Make sure that you can multiply these two matrices together. Now I attempt to find B times A. And I write them out like this. B is the first, B is first, so I write it down first. And I'm going to multiply that by A. I do my size check. This one here is a 3 by 4 matrix. This one here is a 2 by 3 matrix. I check those two inner numbers. Ding, ding, ding. They don't match. This is not happening. So BA is undefined. This is important. Okay, what is important right here is AB not equal to BA. Matrix multiplication is not commutative. Okay, this is not the case like with numbers. For example, if you go like this, 2 times 3, you can always do it as 3 times 2. right? You can always do that with numbers. The arithmetic, numbers, multiplication of numbers commutes. Matrix multiplication is not commutative. This may be the first time you have seen an operation that's not commutative. If that's the case, take note. This is an important difference between these guys and other objects you may have multiplied together in the past. I'm going to emphasize this a bunch in the next few lectures. Okay. Linearity properties. I'm just going to state what it means to be linear. What it means to be linear is if we have a function and we apply that function to c times the variable, we expect the result will be c times applying the function to the variable. If we have a function and we apply it to the sum of two variables, we expect the result to be the same as applying the function to one variable, applying the function to the other variable, and then adding the results together. These two things imply that a function is linear. That is the definition of a linear function. All right. That is what this is saying here. And what we're thinking of here is rather than a function, we are thinking of multiplying a matrix times a vector, or multiplying a matrix times the sum of two vectors. So these are the linearity properties. And what we're thinking here is rather than maybe of the word that we would use before, a function, what we're thinking of is the matrix A is operating on the vector. Operating on X, or it's operating on C times X, or it's operating on X plus Y, where these guys are vectors. Okay, and this guy is a scalar. Okay, so sometimes we're going to see a lot more of this coming. We're going to be saying, okay, if we take this matrix and we apply it to these vectors, what happens? Geometrically, things happen. They rotate. The vectors can rotate or reflect. We're going to see that coming soon. Okay, so in this case, we're thinking of the matrix as operating on the vector and doing something to it. Okay, the most important thing probably we can take from this lecture is, first of all, you should know how to do the multiplication. Secondly, though, really need to grasp these three important points. Matrix multiplication is not commutative. That means that AB is not equal to BA in general. In some special circumstances, it may be, but in general, it is not. These other two properties follow from that, but sometimes I have seen students many times do one of these two things, even knowing this thing here. So let's explicitly say that you cannot do this. The cancellation law is not valid. What does that mean? That means if you have AB equal to AC, just say that's true. This does not mean, it does not mean that B is equal to C. That means you cannot do this. You cannot cancel out the A. Okay, normally with numbers, if you have something like this, X times Y is equal to X times Z. As long as they say they're non-zero, so these are all non-zero, just so we don't introduce any complications, then we could say that's fine. Then that means that Y is equal to Z. That's our cancellation property. We cannot do this. We cannot do this with matrices. So please do not do that. Okay, next one is that if AB is equal to 0, if we multiply two matrices together and get 0, it does not mean that A equals 0 or B equals 0. Now, normally if we had something like this, X, Y is equal to 0, we would then conclude that X equals 0 or Y equals 0 or both. We cannot make that conclusion with the matrices. Okay, let me just give you an example. Here's A. Not 0. Here's B. Not 0. and here's the product, 0. Okay, so don't assume because the product is 0 that one of them is 0. Really important. Okay, the identity matrix. We touched on this a little bit earlier. This is our final thing to say here. The identity matrix looks like this. Here's I2. It's a square matrix. It's diagonal, and it has ones on the diagonal. There's I3. Okay. We've got ones on the diagonal, ones on the diagonal. This guy plays the role of 1 in matrix land. Okay, 1 is the multiplicative identity for our numbers. I at the correct size is the multiplicative identity for matrix multiplication. Okay, it is the multiplicative identity element. Okay, in the same way that 1 works, like if we go 1 times 2, we get 2. If we say 2 times 1, we get 2. When we multiply by this multiplicative identity element, nothing happens. The same thing happens here if we take a matrix A and we multiply by the identity element of the correct size, we get A. If we take the, on the other side, it also works, okay? So the identity matrix is always square. It's always square. It is diagonal. It is upper triangular. It is lower triangular. And notice that both the column vectors of I and the row vectors of I are the standard basis vectors. So when we look at the matrix I2, we notice that these guys are the standard basis vectors for R2. When we look at the I3, we can see that these guys are the standard basis vectors for R3. An important matrix that we often need to make use of. All right, that is it for section where are we? Section 3.1. We'll be back with the next installment shortly. Thanks, guys.